All right, so we're off to 2.5 and we're going to learn about continuity today. The fancy definition of continuity is a function f is continuous at a number a if the limit of f of x as x approaches a equals to f of a. This looks a little crazy, but actually it's not too bad. Mainly just remember continuous means that it exists at all the points. There's no holes. There's no asymptote. It is continuous. It continues. You know the word continuous. But let's look carefully now. F of a is defined. That means there at a here, there is a y value. For this point a on x, there is some y value. If it has it, great, check. Now, does the limit exist? What does it mean for the limit to exist? That means right-hand side and the left-hand side go to the same point. The last thing, are they the same point? Earlier, in the last few sections, we looked at some cases of limits where the limit and the actual y value point were not the same. So at those times, it's not continuous. Then you'll usually have a hole. There might be an asymptote. It would be like jump from one function to another function. But just use your original thought of what continuous means. There's no breaks, no gaps, and you should be okay. But this is how you officially check and prove if something is continuous. And if it's not, then it's called discontinuous at a. All right. Figure 2 shows the graph of function f. At which numbers is f discontinuous? Why? All right, here it is discontinuous. There is an open circle. Here to here, it jumps, so it's discontinuous. It completely breaks apart. Left-hand side, right-hand side, not the same. Here, there's a point at a different place, and there's an open circle here. Definition 1 has 3 conditions. Which condition does it break? Here, it breaks 1 because at that point, f of a does not exist. Here, the limit does not exist because the left limit and the right limit are not the same. And here, the limit exists, f of a exists, but because they're not the same, it is also discontinuous. Okay, so 1, 2, 3. 1, 2, 3. There's special names for them. Removable, A and C are removable because open circle, removable, and it is called a jump here. And this is called infinite discontinuity. So 3 types of discontinuity: removable, infinite, removable, and jump. Jump just means there's a gap. You jump to the next thing. It's not continuous. Removable, like you took away that closed circle, it became an open circle. Infinite, because both sides go to infinity. A function f is continuous from the right at a number a if from the right-hand side it is equal to f of a, and f is continuous from the left at a if the left-hand limit is equal to f of a. So now they're just checking one side and the other side. They're saying it's only continuous on one side, not the other side. We don't know the other side. Okay, and a function f is continuous on an interval if it's continuous at every number on the interval. So you have to check every single point, is it continuous? If f and g are continuous at a, and c is a constant, then the following functions are continuous at a. All right, so that means this is a function, this is a function, c is just a number, constant means just a number. So if we add them, they're still continuous, subtract them, still continuous, multiply them, still continuous, divide them, still continuous, as long as the denominator is not equal to 0, like always. And also if we just multiply the function f with a constant, they are still continuous. So take a look, because you might have some problems that ask you to prove, then you'll need to tell them which law you used or which theorem you used. So you might have to refer back to different definitions or different laws to prove these things. And limit laws were from the last section, so you might have to look at the book from the last section. Theorem: any polynomial is continuous everywhere. That is, it is continuous from negative infinity to infinity. Any rational function is continuous wherever it is defined. That is, it is continuous on its domain. All right, that just means that any polynomial function you've worked with in the past, any rational functions you've seen in the past, there are no holes, there are no infinite discontinuities, there's no removable discontinuities on its domain for the rational, and everywhere for the polynomial function. The following types of functions are continuous in every number of the domains. Okay, so here's a list of all the ones that in their domain there are no breaks. If f is continuous at b and limit of g of x as a approaches a is b, then the composite function, so a function inside another function, is equal to f of b. Okay, so this is b already. You put it in. Then you put in b for g of x, then it's equal to f of b. In other words, you could take the composition of function before or after the limit of the first function, only if it's continuous. If g is continuous at a and f is continuous at b, then the composite function is continuous. Okay, composite functions are continuous if they're both continuous. Intermediate value theorem. Suppose that f is continuous on the closed interval a to b. So here to here it is continuous. Then let n be any number between f of a and f of b, right here, where they're not equal, okay. Then there exists a number c between a and b such that f of c equals to n. And remember, n is any number between here. C is any number between a and b. So that's just saying if there's no break between a and b, there has to be some number c, and that c will have some number n that's between f of a and f of b. That's pretty obvious. Intermediate value theorem just means that there's an x value between here that will have a y value between here, and that number exists. It has to have a number between them. Okay, 2.5.